So, Davian's invited me here to talk about Passivhaus, but to put it into the hacking context, I will be framing it in a way that is going to leave you guys with something to chew on afterwards, and hopefully inspire you to kind of dive in and see if there's something that you guys are interested in engaging in and hacking with me. So just a quick overview of what I'm going to cover today. I wanted to start with who I am and where this journey began for me. I'm not going to give you the full biography. Then I'll go into a quick overview of Passivhaus just to put what I've been doing in context. Then we'll look at California's infamous and historically fabulous Title-24 energy code and how this applies to project development timeline for buildings. And then we'll look at how it's developed, because this is a journey that I've taken out of curiosity and because of the advocacy work that I've been doing over the past few years. And I've sort of come across some really interesting obstacles that I think really have been a big aha for me and might be of interest to you folks here as well. Then we're going to look at, I'll give you some challenges of like how we can potentially hack those to really accelerate the carbon emissions reductions for building, which is really what has driven me to start doing all this work. The mission statement in the bar below here is the North American Passivhaus Network mission statement, which is really to drive industry transformation using the International Passivhaus Standard. So a little bit of background here. Really, I came to all of this work as a practitioner. So I am an architect. I'm based in San Francisco, and for my entire career, I've really been chasing this idea of how to build a really reliably comfortable building for my clients. And this through various explorations. I went down a bunch of different rabbit holes in the early 90s looking for the green building pathway, and we've tried all sorts of things, looking at straw bale and cob and denim insulation, and this was sort of in the era where we really didn't know what a green building really was, and we were all sort of collectively trying to define that idea. And this was where I stumbled across Passivhaus by going to a presentation in Berkeley by a guy named Nabita Hahn, who had recently returned from living in Austria and renovated his bungalow in Berkeley using this Passivhaus performance model. And it really was a big aha kind of eureka moment for me, because it really gave, not only had the integrated methodology to deliver this reliable comfort, but it actually also had the tools. And, as a pretty practical practitioner, I always want tools. So that really struck a chord for me. And it differentiated itself too by being this sort of real long, holistic, integrated approach. And this image always really resonates with me, because I think a lot of us tend to take the business as usual idea. We do the recycled cups, the insulated sleeve, and the plastic lid. That's sort of a minimal plastic lid that can be also recycled. But if you compare it to that insulated mug, that's really just bulletproof, airtight, insulated, durable, resilient, and you keep on using it, you just don't throw it away. It really is where we're trying to go with Passivhaus. And just to give you a quick peek into how this really does work for buildings, we hosted what has become internationally known as the Icebox Challenge here in California. We did this twice. We built 2 boxes with the help of our friends at Laney College, actually. One box on the left, the blue box, was built to standard Title-24 energy code minimum for this climate zone in Oakland, California. And the red box, we built it to Passivhaus standard. So really, it basically, all it had different to the code box was it had a little bit more insulation on the box. It had an air sealing strategy. So it actually had a membrane that could be air sealed, and we did a blower door test to make sure that it actually was tight. The windows were a little bit better performance, so we had much better frames and glass. And we put, you could see on this this red box on the west-facing glass here, we actually put an exterior shade system so that it actually stopped the heat of the sun directly hitting the windows. The light could still come in. And we filled these boxes with 100 pounds of ice. And we sat them outside in LA, well, first of all in Oakland, and then in LA for a week. No mechanical systems, no, no mechanical intervention, no heating or cooling. And we just left the ice there. And you can see at the end of the week, the Passivhaus box on the image on the right still had a good amount of ice. It had almost half of the ice left inside the box. Whereas the code compliant box, by the end of the week, the ice had completely melted. And in fact, the LA experiment was the first time for the Passivhaus Challenge that the ice in the code compliant box actually had gone by day 3. And we also monitored the indoor and outdoor temperatures. And you could see in the Passivhaus box, it was still quite comfortable and cool inside. It was 52 degrees and outside was 71. Whereas in the code compliant box, it was 67 indoors and 71 outdoors. And in fact, we found that actually the code compliant box got even hotter by the end of the week than the outdoor temperature. So it essentially became an oven, which really should tell you a lot about our code has still a long way to go to actually become really resilient. So, and just a little bit more about how this is all kind of transpired in my own work. Because of this sort of epiphany and wanting to really figure out how to get, how to do, apply this Passivhaus methodology here in California, I went on to help found the local Passivhaus California affiliate. And we joined under a national umbrella with a bunch of other Passivhaus affiliates around the country that had sort of also organically sprung up at the time. And I then went on to help found the North American Passivhaus Network, which serves as the sort of national umbrella organization for all the regional Passivhaus advocacy organizations. And we are affiliated with the International Passivhaus Association, this IFA organization, all working under the umbrella of the research and development of the Passivhaus standard that was founded by the Passivhaus Institute. So just to ground this in information about what is Passivhaus and how was the standard developed, I'm going to go into that a little bit before we go into the Title-24 comparison and how that works here. So the original concept is super basic, and in our current COVID constrained world makes so much more sense. It really was based on the idea of how to deliver 100% fresh air into a building without having to, and then just supply a very little bit of heating and cooling. And really, that was the main experiment. And it was founded by two physicists, which sounds like an idea that physicists would come up with. And then, based on the goal of supplying 100% fresh air ventilation to a building, they then looked at what the target had to be, how little heating and cooling had to be, would be required to enable that fresh air supply to be possible. And then they literally designed the rest of the building elements around that goal and figured out how to actually achieve that primary target. So, the baseline really of Passivhaus was they figured out that if you created a building envelope that only needed 3.2 BTUs per hour per square foot as the primary heating load, then you could actually constantly supply it with fresh air. And as I say, in the COVID constrained context, this suddenly makes a whole lot of sense, because if you've been reading any of the science coming out from, how to minimize the COVID spread inside buildings, all the guidance is saying 100% fresh air supply, which is incidentally, where this all started. So, based on that thought experiment and, developing the physics around it, the first Passivhaus was built in a place called Kranichstein in Germany. It's just south of Frankfurt, for any of you who've ever been to Germany. And this is it. It was a fourplex, 4 townhouses. And one of them is owned by the founder of the Passivhaus Institute. He lives in the end one on the far left there. And he then founded an institute and developed an energy model that can be used by anybody, including myself, architects, to achieve these targets in your local climate and with whatever building you care to input into the software. And incidentally, I developed a tool with some smart physicists here in California a while ago that looked at how do you do sensitivity analysis to your energy model to really optimize the targets that you are trying to meet for all of your components of your building. So your windows, your exterior wall assemblies, your roof, your mechanical system, how beneficial is air tightness in your climate, and then a couple of other sort of very specific window surface area, etc. And I ran that original Kranichstein building's Passivhaus model through this sensitivity analysis package, and lo and behold, found that every single component in that building was optimized to that 10 watts per meter squared, or 3.2 BTU per hour per square foot heat load target. So clearly, very meticulously developed and designed. So, once with the big picture in mind of like what Passivhaus is all about, which was originally the goal to deliver what's commonly now known as hygiene ventilation, which is just basically 100% outside air supply to your building, and then being able to heat and cool that minimally without using too much energy. These were then extrapolated to become the Passivhaus standard. So you could certify your building, and the primary certification metrics are these. So the peak heat load number of 10 watts per meter squared, which is, I've shown you where that and how that originated. Then they set a heating or cooling demand cutoff point, which just helps really lower the amount of renewable energy required to heat and cool a building. There's an air tightness number, which is really very important for not only maintaining the efficiency of your ventilation system, but also some durability, has some real durability benefits with moisture transfer through walls, and really just sort of containing your indoor air quality within the building envelope, so that you can really effectively filter and exchange air without having random air leaks within your envelope. And then there's a total energy maximum that you can, a target that you have to meet. There's a threshold. And this is historically been this 120 kilowatt hours per meter squared per year, or 38 kBTUs per square foot. And that has all been supported by, as I mentioned earlier, providing a tool that enables anybody to input their building into this model, and then change and adjust the design in the model to ensure that you would meet these certification targets. And so it's effectively a really great design tool, which is what I've really come to appreciate about it. And then they also developed some trainings around the software and the protocols and the methodologies to actually achieve these targets. So it's sort of a really well structured process where you get trained, you get the tools, and then you know how to meet the targets are clear. So actually implementing something that's actually could be quite challenging has a support structure for implementation. And then, as with anything good, it evolves over time. And so the original standard, this total primary energy target, in 2015 was actually completely overhauled, because our world has really changed quite dramatically since the early 90s, when this standard was first developed. And the carbon emissions and our climate change challenge has become really one of the biggest imperatives of our time. And making sure that the total amount of energy that buildings consume aligns really well with renewable energy generation was really what prompted this overhaul, to make sure that what we built actually can be run on a completely 100% all renewable energy grid. And it's actually become quite a fascinating review of how to build grid optimized and supportive buildings. So without going too deep into the weeds, 3 specific energy classes were, new certification levels were developed, each of which can integrate on-site renewable energy generation. And the third one actually also allows for off-site renewables, such as wind farms that are specifically tied to a project. And as I say, the 3 classes are really they're a function of reduced demand over increased generation. So they're a sliding scale as opposed to a fixed target. And they're a classic is the basic passive house that can have some renewable, but it needs a specific amount of renewable to get to the second tier class, which is the plus energy. And the third tier class is the premium energy. So it's maximized demand reduction and maximized renewable energy generation. And of course, the plus is sort of an improved variant of the premium and the classic. But, you know, needless to say, the basic premise of Passivhaus remains, which is drive demand down to the lowest possible point to make it, you know, to be economically feasible, then optimize the amount of renewable energy that is supplied, and reduce any non-renewable energy demand. So it doesn't say you can't use a fossil fuel, but it heavily disincentivizes them, and basically penalizes the fossil fuel supply grid. And then it gives you some options for green roofs and shaded roofs. You can do on-site renewables, but you can also do off-site renewables. But essentially, your roof also doesn't have to be used for renewables. It can, you know, you can put the renewable generation elsewhere. So it also has a framework for retrofits, because as everybody who works in the building industry knows, most of what we will build in the next, you know, most of the carbon emissions from buildings are coming from what's already existent. So being able to create a framework that allows for existing buildings to also be upgraded and also meet these same rigorous energy targets is important. The metrics are slightly more relaxed for retrofits, because everybody understands that retrofits are a lot more challenging, and you're dealing with a lot more constraints that you don't have so much with new construction. And the retrofit process can also be done in a phased way, to where you can actually do them in you know, phases, so that the economics aren't as challenging, because sometimes you just don't have all the money up front. But being able to do them in a mapped out version with a plan, and you know when you can afford to do each upgrade and still meet the end goal is important. And there's a couple of different methods, pathways to do that. So Passivhaus is also a global standard. It applies to all the different climate zones across the globe. And in California, here, Passivhaus California has had all the 16, we have 16 different climate zones in California, and we have had the climate data set modeled for all 16 climate zones here in California. And essentially, you simply adjust the design of your building to meet the targets specific for your climate zone. So obviously, a colder climate zone like Tahoe, you would need slightly thicker walls, a little bit more insulation, and perhaps you know, definitely triple pane windows. Whereas in San Diego, you might actually not need any insulation in your foundation, because you want the cooling, you need the cooling benefit of being ground coupled, and you definitely don't need triple pane windows in San Diego. So as I say, it's design adjustable to your local climate zone. And currently, this is a map of, you know, there's a database, growing database of projects that are certified or have been designed to Passivhaus around the world. You can see it was originally sort of really propagated more widespread in Europe, but it's growing rapidly and spreading around the world. And these are some of the buildings in various climates. This is a factory in Sri Lanka in a hot, humid climate. This is a bank in Vienna. Two existing buildings were retrofitted and a new tower was built. This is the first Passivhaus tower in Vienna, office building, obviously. This is in New York. This is a dormitory on the new Cornell Tech campus that was at one point the tallest Passivhaus in the world. There's a fire station in Frankfurt, and this is a medical clinic in Spain. So enormous variety of building types that can all be built to Passivhaus, as well as retrofitting of historic buildings. So brownstone in Brooklyn, Craftsman in Santa Cruz, office building in Austria. This is a building in New York City, and this is a bungalow in Sonoma. So really flexible application. And then Passivhaus is also being implemented at a very broad scale in entire neighborhoods and cities. Brussels transformed its built environment in 2015. Actually, from 2007 to 2015, they went from being the worst buildings in Europe to actually then by 2015 having their building code be the equivalent of Passivhaus. So it was a rapid transformation of their built environment, using a really smart policy implementation process. Cities in Europe are also creating entire Passivhaus neighborhoods. This is Bahnstadt in Heidelberg, is a redevelopment neighborhood from an old train, what would it be, like a loading yards, pretty much like Hudson Yards in New York City. This is a whole region that every building in that neighborhood is required to be built to Passivhaus. And then even more mind-blowingly fantastic, I had the pleasure of being in China last October and visited this city outside of Beijing called Gaobaijian, and they have built an entire city to Passivhaus, which is also pretty radical. And you know, my head was exploding going all around there and seeing how that was being done. So essentially, you know, Passivhaus is being really transforming how buildings are being built globally in many places. And California has sort of had our own small following and uptake of using this methodology and implementing this. We published a book in 2016 with a bunch of passive houses around California. But you know, we actually have found that California has slowed down a little bit compared to the uptake in other regions. And this is sort of really where, you know, I'm just showing you some projects that we also have on our database all around California. For the most part, the uptake has been in single-family residential buildings. And this is also where, this is the space that I've been working in. And, you know, this really, as an organization, as Passivhaus California, we sat down and we looked at, you know, why has California been slower to pick up on Passivhaus than many other regions around, not only North America, but definitely the globe, because, you know, California has historically been leaders and innovators, and our climate policy has also historically been very well regarded. It we are a leader in our big picture policy, and our state climate action goals are very well regarded and great. And when we started sort of looking into that sort of policy framework, how policy gets implemented here in California, and we started to look at our particular projects, and I started to look at my own, and this is a house, not sort of a design magazine worthy house, but not a terrible one, I hope, that I did in Alamo for clients who wanted a colonial revival style. And so I designed this house for them, and started really documenting like how this stacked up. How does my passive house design stack up against our California energy code, which, for those of you familiar with it, it's a requirement for every building in California to be run through a comparison energy model to obtain a permit, and every building, new and retrofit, has to meet certain energy efficiency criteria. And to be honest, all of my designs, I had always just designed them, and at the end of the design, before I get the permit, send it off to an energy modeler and have them crunch the numbers. And then, usually my buildings were fine, but really was a very detached process, and I had really no control over, or any feedback loop about how my buildings were really performing. And once I started doing Passive House and really owning my own model and operating, modeling the building in the Passive House energy model during the design phase, where I could really then tweak the systems and the assemblies, that gave me a much more ownership of the efficiency of the building, the performance, because really, as I mentioned in the beginning, delivering that comfort level was what I was really was what was really driving me to explore this avenue. And so this is the monitoring data for this project. We documented the production and the energy use. So it's the building, the total square foot is, it's a 29, it's just under 3,000 square foot building. My energy model dings that a little bit because it doesn't calculate some of the areas and the thickness of the walls. It's just the conditioned space. This is the net annual energy use, and this is how much the solar array, the 7.5 kilowatt solar array produces. So you can see it's a net positive, it's a net positive home. It produces way more than it actually uses. But when I started to look into, and this, when I looked at what was required by code, this was the 2016 code that was, oops, let me go back here. The code required my roof to be an R38. My Passive House model, I built it at R46. It could have been just a little bit less, but we just filled up the entire roof cavity, and effectively the R value is 46. My walls code at the time required them to be R19, and we built them at R28. My windows, you could see, are much better than the code requirement, and we insulated our slab, whereas the code does not require that slabs are insulated. And we also, the code assumes an air tightness of 3 air changes per hour, but incidentally does not require that it be tested. So that is a very, wishful thinking requirement as far as I'm concerned. We tested the air tightness of this building. It came in at 0.3 air changes per hour. And just to put that in context, the Passive House standard requires that your building meet 0.6 air changes per hour. And an average building tested in California ranges between about 12 air changes per hour, and some of them get down to 3 or 4, but generally, you know, 0.3 is considered incredibly air sealed and a tightly built envelope. And of course, we included a mechanical ventilation system in here with heat recovery. So again, with this 7.5 kilowatt array on the south facing roof of my building, and actually this owner also has an electric vehicle. You could see the house used just under 10,000 kilowatt hours per year. They used some for the car, and we had a net positive surplus after the PV production. And for those of you who understand energy use intensity, the energy use intensity for this building is at about a 9.5, which is within the Architecture 2030 target range for a single family home. But what I found, the idea of this net positive or even net zero house became really problematic once we started to look at this building. The energy use over the year, you know, on an annualized basis, and looking at the use versus the generation, because as you can see from this monitoring data set down below here, the red is the outdoor temperature, the blue is the solar production, and the green is the consumption of the house and the electric vehicle. And this disconnect, the dissonance between the production and the use from the generation, is really the challenge that we are facing, because unless you are also going to be requiring that every home install batteries, which changes the economics of efficiency radically, but it also changes the usefulness of this net zero approach, because in reality, this home is incredibly efficient compared to its neighbors. So it uses about a quarter of the amount of energy per year. But more importantly, at this period of the year between November and March, the winter period, it still consumes more than it generates, which means the grid then has to step in and supply this home with additional energy. And that is always the time of year when the grid actually has the hardest time generating renewably supplied energy. So this is really what we should be looking at in a much more rigorous and thoughtful way. And even, you know, as I say, even if I build to passive house, I'm finding that my house still cannot supply all of its energy throughout the year, and the net calculation becomes very problematic. And just to demonstrate, this is another house that I built more recently and did the same monitoring, because really once you start monitoring your projects, you really get to know like exactly how effective your strategies and your energy model is working. And this house is an incredibly efficient home. The green line is the energy, the total energy consumption, including with the electric vehicle. The owners have one electric vehicle they charge off of this solar array, the arrays on the backside of this house. This is their solar production. So you can see again in the winter, and in fact, there is, interestingly, a small dip because of our summer fog in the solar production that happens in the July-August months, where it doesn't quite supply all the demand even. And this is, I managed to find through PG&E, all the homes in this neighborhood were all built the exact same model with slight variations, but essentially all the sort of 2-bed, 1 bath, 1 garage, bungalow cottage. And I aggregated all of those and showed this is the average energy consumption for a similar home in the same zip code. And you can see this huge discrepancy. If and these were old. Some of these houses had been remodeled, but not all of them. And even if it was halfway, the consumption for this house was the other houses in the neighborhood were, half as efficient. You could see a much bigger discrepancy between consumption and production. And so back again to where I was starting to see big disconnects between what I was trying to do with Passivhaus and what our Title-24 energy model was pushing us to do, started to become really much more apparent. And so this project, this was my Passivhaus metrics and model, and these were my, the results that my energy model told me I was achieving. And then my Title-24 energy model, these were the results that it's very difficult to actually, I really struggled to be able to put it onto the results onto this graph in a meaningful way, because what Title-24 does is it doesn't compare, it doesn't give you the absolute targets for your building. It compares your building to a baseline building, which then the results are, you get told my building was 57.5% better than this mythical baseline building, which incidentally is not anywhere close to what my design looks like. And that was for space heating. I was 23.9% better for space cooling. I had some IAQ ventilation numbers that it said I was 0%. And this was because I installed a heat recovery ventilation system, and in the 2015 Title-24 energy code, it was just simply not possible to get any credit for that, even though it's a incredibly much more efficient piece of equipment. And for water heating, I installed a heat pump water heater back when, before everybody was on the electrification bandwagon. And again, the Title-24 energy code software was unable to give me any credit. So I got 0% improvement for that. All of which is to say, what we've been doing in the Passivhaus world has always been sort of leaps and bounds ahead of the code, which, in itself is not an indictment of the code. The code has always been basically designed to prevent the worst building from happening. And it really doesn't have any real bearing on where you should be going to achieve the best building. And we are finding that incidentally is still the case. And so when people always tell me, oh, well, California has the best energy model and our Title-24 is wonderful and it's really hard, I'm always kind of a little bit more, I temper that enthusiasm, and I do, want to give it credit for having done great things. But I still also say we actually have a lot more room to improve, and our Title 24 energy model is still only just the best, the lowest performance building that is legal. So this was sort of where we went to. This motivated a bunch of us working in Passivhaus in California to sort of dig a lot deeper into policy and how Title 24 is developed, and kind of get involved in that process a little bit more to see how we could help use the information that we had gained from building passive houses in California, since many of us have been doing this since 2007, and help influence code in a good way. And that journey upstream in the policy process has been really fascinating. And so this is sort of where the hack part comes in, because what we found as we started to engage with the code development process was there are good overlaps between Passivhaus and how Title 24 code evolves. And we could intervene to some degree and comment and provide input and feedback to the code development process. But there were also things that really were completely outside of the code framework, and really haven't started to be addressed in a real integrated, holistic way. And so I created this slide to really just give a very graphic overview. California Energy Commission hosts workshops throughout the code development process, and they are bracketed into these categories. So when they are looking at the residential code cycle for the next code iteration, they'll host a workshop on envelope measures, and similarly another one on glazing, so your windows and doors, another one on HVAC, so your heating, ventilation and cooling, so your mechanical equipment, and then water heating. So sorry, that's a typo there, I should have made this, that should say water heating, and lighting. So, and these are the basic categories. And what we found in commenting on those is we really were prevented from being able to engage properly and provide any hope of making the code go closer to Passivhaus because of the siloed framing and structure of how the code is developed in California. So for example, for Passivhaus, air sealing is really one of the core tenets, and measures, obviously it's a certification requirement to get to this 0.6 air sealing. And we found there was really just no place for us to advocate for air sealing. But more importantly, if we advocated for air sealing and then we didn't simultaneously advocate for mechanical ventilation that would allow that building to still remain healthy, and we couldn't also simultaneously require thermal bridge detailing and elimination, we would potentially be advocating to create a really potentially toxic and dangerous building. Because if you do air sealing and you don't actually eliminate thermal bridges, you could be creating cold spots on in your building envelope that would be places for mold and mildew to grow. And if you don't simultaneously have a good ventilation system, you could be creating some really bad indoor air quality. So what this really evolved into was this fact, this realization that with Passivhaus, what you have is a very holistic, integrated process where every one of these elements has to be designed in conjunction with the other elements in order to meet this very clear, defined target with the goal of this meeting this hygiene ventilation criteria. Whereas our Title 24 code structure has these very siloed buckets where you can intervene and advocate for improvements, but none of them necessarily connect with each other, and they don't create a holistic approach to building that optimizes the integration of different systems. But more frustratingly, what we also realized was because of the way Title 24 is developed, where it's a 3-year code improvement cycle, where every 3 years a new code comes out, there's actually zero transparency about where our code is eventually going. And this, for both a building designer and a developer and a product manufacturer, is a complete disaster. Because this lack of clear targets and transparency in where we're going is a business catastrophe. This is the only industry where we have no foresight about where we're going and where we need to go. And this, I have to say, was a real, like, a head exploding moment when I looked at that and said, wow, no wonder our industry is completely chaotic and in disarray, because if we have no directional guidance of where we really are heading, this is just a killer for the development of really awesome products and innovation. So, you know, that really was the big aha slide. This is my $1 million slide that I'd like to really focus on and drive home. And then what I also sort of looked at, this is a really terribly graphically laid out, I apologize, development timeline for buildings. And it also really showed me that Passivhaus is a much further upstream intervention. You cannot do Passivhaus at the end of your design development because it just is really hard and expensive and you don't optimize your design. So in your design development, you know, right up front at schematic design process, you have to do your preliminary energy model, and you use your energy model to optimize your design and tell you what you need to do to ensure this hygiene, ventilation, and excellent comfort. Then you develop your construction documents. And this is historically when most Title 24 energy calcs get done. At the end of the design, where everything's already locked in and your opportunities to optimize are really much more limited. So this is upstream versus a downstream solution. Then you get your permit and you go out and you build your project. Both Title 24 does now have site verification. You do have to be, you know, your building inspector will look at your building to make sure that you have implemented the efficiency measures that you have documented in your energy calculation. And so does Passivhaus. This is where Passivhaus blower door testing is required. Your HERS rater will come out and check that all your insulation is installed the way it's been documented and required in the energy model. And then the documentation for certification for Passivhaus is really usually happens after the building is complete, so that all the documentation can be vetted against the model, and the certifier can then say, yes, you meet it, or no, sorry, didn't quite cut it. And then the plaque is issued, or the certificate at the end of the process. So if we go back to where we need to, you know, where we need to go in California to actually allow for this holistic upstream design thinking to be able to integrate that into our building process is kind of what I wanted to bring and share with you today. And California, as I mentioned, has some fantastic policy, high-level policy, and our buildings are now being required to meet a carbon emissions target rather than a simple energy use target. But the transparency of what that actually means for the user, the practitioner like myself, has been very challenging to uncover. And you know, I pride myself on being a little bit more familiar with this process than most architects. I think I'm still kind of the anomaly in the design world, where I'm a lot more connected with the energy and the design and the carbon emissions for my projects. And you know, it's just because I'm curious about that. And you know, no aspersions on other architects out there. There's plenty of things that architects are required to still manage, but we should be making this easy. And this is a slide that the California Energy Commission put out a while ago, showing for our grid when are our most carbon emissions intense hours. So it's a 24-hour block and then a month, and it's starting from 2019, so last year, as it relates to our current energy grid to where we're heading in 2030. And so as our grid electrifies and becomes much more supplied by renewable source energy generation, you can see the carbon intensity of it actually improves. And you can see, incidentally, you can see right now we have renewables on the grid, and this is the lowest carbon intensity generation happening during the, you know, from 8 till 9. So this is obviously wind and solar. And you can see as the grid becomes more renewably supplied, the grid gets greener and greener during the middle part of the day. But it's the night part of and the early mornings that become still, you know, fairly carbon intensive. So what I'm really trying to convey with this, again, is going back to that slide that I showed of my project, two of my projects. Really, we're designing for the time of year when the grid is most hardest to supply with generation, and at night. And I'm running probably a little bit over time here, but I've got a few more slides left. Really, what we found, we did a proposed REACH code at Passivhaus, California, and we looked at, okay, if we did integrate Passivhaus into California's energy code, where would we start? And what we did was we started with low-rise multifamily buildings, not because we were all familiar and practitioners in that type of building. As I showed earlier, most of us were work primarily in the residential single-family home arena. But we saw that low-rise multifamily buildings were much easier to become really energy efficient and cost-effectively built to Passivhaus. So we started with that building type, and we generated a REACH code for Santa Monica, where we modeled a standard low-rise multifamily building in all 16 climate zones in California. And the results of the study were remarkable. What we found and what was confirmed by the case organization, the case group that vets the REACH code and verifies that they can be adopted, showed that a passive house model, the all-electric, were leaps and bounds more efficient than the REACH code target required for 2019, and in some cases 700% better, which just completely blew my mind. Like, how is our REACH code for Title 24 that far off from what we found in our study? Was not a major improvement. The study basically found that in pretty much all climate zones, if a low-rise multifamily builder installed a heat recovery efficiency ventilation system, they would no longer require any heating equipment installed in the building. So the measures were very minimal, but had these massive improvement on these EDR margins for all these climate zones. So that also made us realize that there were big blind spots in our code development. Oops, I have my my slide is a little bit out of order here. But essentially, let me go back to this. What we found were these blind spots in the Title 24 model, where we showed that, passive house, because of this holistic integrated approach to buildings, can create significant improvements in the output and the carbon emissions reduction for building for very little additional money. In fact, Pennsylvania has developed a program where they've now shown that passive house buildings can be built for 3% less than a code compliant building. So there's no reason that this is cost prohibitive. We also saw that the energy model currently used in Title 24 has big blind spots. It doesn't credit air sealing adequately. Thermal bridges are not calculated. Exterior shading there's no opportunity for them to be inputted. And as I said, heat recovery ventilation is very unexplored, and something, given our code, our current COVID state, where we know that supplying outside air continuously is much more beneficial for our health than the recirculation air systems that are currently much more predominant in our buildings. So I've got 2 more slides, but I really also wanted to show the other thing that became really apparent is that, in California, we've been really good at developing smart tech. All of you understand how the integration of multiple components into one optimized system, simplified, has really exploded how California's tech industry has developed. And, we are still global leaders in this arena. Yet the construction industry, I'm kind of become well known for moaning that I say that we are still currently in a third world product market for construction industry equipment. And so these are my wish list for you as hackers in this space. If you're not going to be helping hack policy, what we really need to be also doing is starting to hack construction equipment, and there's huge opportunity for this to happen here in California. This is equipment that I see when I travel elsewhere. The Chinese were building these amazing integrated boxes where I can have my hot water heating, my heat recovery ventilation system, and my heating and cooling all integrated into one really simple package. I desperately need this for my apartment here in San Francisco. I want ventilation and I want a heat pump for heating and cooling. But I really am much more interested in that fresh air supply. And I just simply can't access this equipment. So as a hackathon opportunity, if you're not interested in policy, get into the making of this integrated equipment. It's a huge gap in our market. And I would love you guys to see how to engage and deliver this equipment, which really has become ubiquitous throughout the passive house world, except for here in the US. So closing, thank you so much for inviting me, Damon, and the AEC Hackathon community. It's really fun to engage with you. Let's look at how to accelerate the design of integrated whole building approach systems that accelerate the adoption and integration of renewable energy supply. And so my last slide, if there's anything that you guys can hack, please go for a performance-based code with a very specific target. So none of this like percentage better than nonsense. Use an integrated performance model. I don't care if it's not passive house. I do care that it works. And again, let's look for and accelerate the development of HVAC equipment that shares resources just the way, same way as our smartphone does. So that's it. And feel free to send me questions. My email is down here, Bronwyn@naphnetwork.org. Thank you so much.